Hi guys, how's it going? So today actually we're gonna be going through distributed training in machine learning and deep learning. So this will be more like a series whereby this in this video we're gonna be focusing more on the techniques that are being used, and in the subsequent videos we're gonna look at uh, these techniques, how they are being implemented from a practical standpoint. So yeah, without wasting any time, let's get into it, right? So large models as it follows the Moore's law, so they double every 18 months. So because of this, essentially it becomes quite difficult to be able to train these large models. For instance, we have GPT model which has like 175 billion parameters, and we can convert this into like the training time. We can see that it will take us 3 million hours to train this with flat distributed training. Converting this into years, we can see that it will take us over like 342 years, right? If you can go to AWS and get like the Tesla V100 server, you'll see that it will actually cost you $6 million to train this model. So what motivated me to create this video was essentially the impact distributed training has on like the deep learning community and enabling us to train these large models. For instance, you can reduce the training time by quite a large factor, and while you're still maintaining the same accuracy, right? Which is quite something. I think it's mind blowing. However, there's been quite a lot of work that has been done in the industry so far. For instance, DeepSpeed, which is a library by Microsoft, and also NVIDIA produced Megatron, whereby they introduce. We're gonna get into like their techniques, Tensor One, and Google also had a GPipe mesh TensorFlow. Facebook also had their distributed training framework that they released. So yeah, we're gonna go into like what are the techniques that are behind these libraries, frameworks, what are the things that they've been used to enable this. But before we get into that, I want to start from the hardware perspective and how these machines like servers communicate to one another, right? So you can think of like we have a host, and you can think of a host as like the main device on a communication network, and we have a port which can refer to a master port on the host, and we have something called rank, whereby we have a unique ID given to the device in the network. So I know that might be confusing, but if we look at like a visual, let's say we have two nodes, like node 0, it has like 4 GPU, and we have node 1, it has 4 GPU. So when we launch a distributed environment, essentially we're going to end up having 8 processors, which will then be launched. So how is this so? This is possible because we essentially assign a host IP address and a port to a machine. It could be node 1. So then all of these other processes will then communicate to one another using that host and port ID, right? So now that all of these machines are connected to one another, they can communicate to one another. We call this a process group. So you can think of a process group essentially as a communication network which include a subset of devices. And this can occur in different ways, whereby we have a peer-to-peer, whereby one process sends data to another. We have a collective, whereby a group of processes perform operations such as gather, scatter, and all reduce, which are the techniques that we're gonna get into in more detail as we continue. So what do we end up with is that we end up with this thing here, whereby we have a process ID, we have a rank, node index, and a GPU index. So kind of like represent our rank. So this is from a hardware perspective, how these machines are communicating one another, and but then now I want to walk you through like how we then like distribute models, like how is this possible? How do we then take the data and distribute it across these machines? So I want to get into those techniques now, right? So I'm going to start with the main techniques that have believe that this is where we started. So the first one is the data parallelism. So you can think of data parallelism essentially as like we try to split the data into several shards, and each shard is allocated to a device, right? So each device will hold a full copy of the model and train on that shard, right? So what I'm saying here, if we scroll down, is that you can think of like we have a training data, right? We have a training data, and we split this data equally across these machines. But our model is being replicated across these servers. So, we replicate it here. And we have something we call it parameter server, because we know we'd have to do a forward and backward path. Then this server is going to sum and aggregate the gradients that are coming from these machines, right? So that's what it does at the high level. Then we have another technique called model parallelism. So this technique, we say that with different machines, right? Same thing is here, but instead of like putting the whole entire model in one machine, we rather split the model into like different layers. You can think of this as a layer 1, layer 2, and we put that layer into like its own process. It could be a GPU and something like that. Then we forward pass the data. Okay, so what are the key main difference between these techniques? So you can think of it as like the data parallelism, we split the data in copies of models. These models, as we split them, they are the same, like it's just a copy of one another. Whereas with like model parallelism, we split the models into like weights, not necessarily weights, layers. I think the weights we're gonna get into it's tensor one. So that's how it works essentially at the high level. Okay. Now I wanna deep dive into this and explain all of these concepts in more detail. So data parallelism has a concept of parameter server. So you can think of this as like as a server that receives. So its job is just to receive the gradients from all the workers. So the workers, I'm going to explain them now, but this main responsibility is to receive the gradients from all the workers, and then it aggregates them and send them back so that these models in these workers, can update their weights. Okay, so this is the central control of the center of like the training overall. So how this works is that we have a training data set, right? You can think of this as a training data set, right? Which we split randomly and but evenly across these workers. So we have a pool of workers, and each worker here is holding a copy of a model, right? And it then it pushes the gradients to the parameter server. So the parameter server, what it does, it has to update the weights. Then it pushes the changes back to the worker nodes, and this continues and on and on and on and on. But by on and on, I mean what's happening is that if like you can think of these steps as a for loop. So we firstly replicate and pull gradient from the parameter server, right? We sample the data set across all of these worker nodes. Then these worker nodes, they compute the gradients. Then we push those gradients to the parameter server to sum and aggregate. Then the parameter server perform the gradient steps, right? Like the gradient step is like the updating of the weights, right? How will this happen on one server if we didn't have like these number of workers? So if it was on one server, we'll sample the data, compute a gradient, perform gradient steps, right? So that's how we'll go about it. So, but I want to talk about the core challenges now of the thing that we just spoke about, the parameter server. So as you might have realized, what if we have like quite a lot of nodes, like we have a lot of nodes, right? And we're gonna keep sending these gradients, like on and on, back and forth, and Gradient is going to be pushing all of the changes to also the worker nodes. So we essentially going to face the problem of bandwidth requirements, because we can see that essentially the parameter server will have to, it's going to scale linearly with the number of nodes, because like all the nodes have to send all of that. So it's going to be quite I think the bandwidth is going to be of n, so it's going to be quite hectic to manage that. So looking at this from a practical standpoint, let's say we're training ResNet 50 on like V100 server, so we know that ResNet 50 has like 24.4 million parameters, which we can translate to 97.5 megabyte of storage. So for us to do a forward and backwards pass, it can take 3 iterations per second. Okay, so if we have 256 nodes, so we will take 256 times 3 iterations per second times 97.5 megabyte, which will then give us 73.1 gig per second. So this is like the bandwidth that our parameter server will have to support, which shows like how expensive it will be. Hence, like having, and if you increase the number of nodes, like if you add like 300 here, you will see that the bandwidth then increases, right? So that's the point that I'm raising, is that the parameter server essentially can be overwhelmed by the number of nodes that we have in our cluster, right? So can we still achieve distributed training without a centralized server, right? Is there any some sort of like a technique that we can use to avoid the parameter server? So there've been quite a lot of techniques that have been introduced. The first one is the send and receive. So we send different tensors to like nodes, and we can receive tensors from different nodes, right? So this can be deduced to the popular method, they're also known as scatter and getter. So essentially what you think of scatter is that we send tensors to all the workers, right? And with getter, it's like we receive the tensors from like all the nodes, right? So I know this might sound like, okay, this is still parameter server. Yes, because we have to send all the tensors to all the nodes. It's like you can think of it as like the parameter server has to send all of those changes to all the nodes, right? And here all the nodes has to send all of those the gradient to one server, right? So continue on this, we have reduce and all reduce techniques, right? So all reduce, what it does is that it tries to say, can we say for one node to send all the gradients to all the nodes, right? This essentially is going to give us the time of O of 1, because essentially each node is sending all of these gradients to all the nodes in the server. However, you can see that in terms of the bandwidth, it's going to give us O of n squared, because each node is getting all the gradients as per the number of all the nodes in our cluster. So it's quite expensive on the bandwidth, but the time is quite good. Then we have reduce, which is similar to getter. So, but we have this averaging and summing during the aggregation, right? So we receive all of these gradients from different nodes, and then these nodes then have to average them, right? So it's still O of n, because this bandwidth still, you have to receive all of these nodes from all of this, right? So the bandwidth grows linearly with the number of nodes that we have. So okay, let's jump deeper into the all reduce. So there's a sequential, some people they call it naive, all reduce implementation, whereby we say that, okay, for each node, what we're going to do is that we're going to send all the parameters to all nodes. Then in step 2, we choose another node, we send the parameters to that. In step 3, we choose another node, we send it. But this is still bad, because anyway, each node has to receive O of n, because you're receiving all the parameters from all the nodes in the cluster, and this is going to be O of n time, because it's a sequential thing. Like after this, you have to go to another node and do that the same thing. So I think that's why they're calling it naive. So I think we're gonna look at that. This is what we call a sequential all reduce. So we're gonna look at the ring. So the ring essentially tried to overcome the bandwidth problem, and it tried to overcome it by saying, okay, can we say this node send, right? So send the gradient to another node. This one compute, send to another node. This one compute, send to another node. So this way we know that this node is not getting like all the gradients from all the nodes in our cluster. So it's only receiving it from one. So this is essentially give us the O of 1 bandwidth, because we know that the node will never be overwhelmed. But then the time becomes expensive, because now we have to sequentially go through each node. So it becomes O of n. Okay, so like I covered the all reduced parallel. So this one is like all the nodes are sending, all the nodes are sending all the gradient to all the nodes so that they can be computed. It kind of like help us on the time, because but then their bandwidth becomes worth. So all our nodes are getting overwhelmed. So the point here is that, can we again come up with a mechanism? Can we combine the advantages of these techniques that we explained? Can we just like maybe combine all reduce ring to get the advantage of bandwidth? Can we combine the all reduce parallel to get the advantage of like the time, or something like that, right? So we can, which we're gonna use the recursive halving all reduce. So you can think of this as like for all the n workers, all reduce finish in log n step, and the node bandwidth is O of 1. This is mainly because these two nodes, they exchange their gradients, and they aggregate. Then after then they go to step 2, they change with this, and you see that there's two communication between this and this. So this is O of 1 bandwidth. And the second thing is that in terms of time, we don't have to go through each element. We communicate. How can I put this? So I want to explain it in an easy way to understand. So let's say, let's say like you have a pile of apples, right? You have a pile of apples, right? And you want to count how many apples there are there. Right? One way you can go about this, you can say, okay, someone count all of them, but this will, we all know this is going to take too much time. So in efficient way, we can say, okay, how about we have multiple people to count them? Like you can think of servers. We count them into small piles, like, someone counts this, 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 right? Then the two people, they tell each other how many they have counted. Né? Then we add them. So this one says, okay, I have added 2. I have added 4. I have added 6. I have added 8. I have added 2. Né? Then what we do is that we then match these two. We match these two. Right? This one. Then we go again. Tell us the total between these two. To say 6. We get the total here. I think it's going to be 14, right? Then you get 2. Then you match this, just like that, right? So that's how essentially this technique it works. So, and you can see that it's n log n. It's log n, sorry, because we divide by 2 every time. We have to do the computation, right? And the network bandwidth is O of 1 because each server does not have to communicate with all of them. So yeah, that's like the halving recursive. It's quite efficient compared to all the other ones that we spoke about. But that doesn't mean these other ones are not being used. Like if you can go to Colossal AI, they're using some of the older choose techniques that we mentioned about. So we went through into too much detail into how the data parallelism work, but the data parallelism has its own shortcoming also. So for instance, we said that with data parallelism, we want to distribute our model into copies according across our nodes servers, right? But now the question becomes, what if now the server that we want to serve our model actually does not cannot like the model is too large and it cannot take the model. For instance, uh, we know that GPT has something like what is the 5 billion, right? Billion, right? 165 billion parameters. I'm going to multiply this by 16-bit. This is going to give us close to 350 gig, right? And now using the best GPU like it's NVIDIA 800. So 800, which has like 80 gig, right? This GPT model, it wouldn't fit in our server. So here you can think we have 800. So and we want to copy the GPT model into the server. It just wouldn't fit. So hence, we're introducing this model parallelism. So the idea between model parallelism is that we said that we split the model into chunks, and we take those chunks and we distribute them to our servers, right? So for instance, we have a GPU one, we put the layer, we put the layer, we put the layer, we put the layer. For instance, if now you take GPT and you divide it by probably 8 4, you can reduce this to 46 gig, right? And this 46 gig can now fit in our 880 gig, right? So that's the point that we have to split this model, and by splitting that model into layers, we call this model parallelism technique, right? However, there's certain things that we lose as we do this. With data parallelism, we're able to use all of those nodes, like all of every computer was like literally uh, processing the data. But now with model parallelism, because of how we train models, is that we can think of it like we have a forward pass, right? And we have a backward pass, right? So we need to pass. We're going to start from a forward pass and we go to a next forward pass, which is a next GPU. Then we go to the next forward pass. We go to the next forward pass. But can you see the problem? The problem is that while this one is computing, this one is waiting. While this one is computing, this one is waiting. This one is waiting. While this one is computing, this one is waiting. This one is waiting. This one is waiting. So you can tell we call this underutilization of resources. So it becomes a problem because now we are sequentially computing still a distributed training whereby the model now can fit in the server, but then it's gonna take time because now we are underutilizing the resources. So this is what we call a naive model parallelism, right? Whereby we divide the model into partitions and assign them to different accelerators. But now, NVIDIA said we can rather like, because we know that we don't update the model in a batch. So how about we take a batch, right? We take a batch and then we split it into macro batches, right? So this way we get to utilize more the accelerators more, right? So the intuition here is that when we train in a single batch. We don't update the model, we don't update the weight. So this is the time whereby we can probably leverage that. So from a visual perspective is that we then say, okay, cool, this is going to be macro batch. We put it here. This is going to be a macro batch, macro batch, macro batch, macro batch. We put it here. And now this, yes, there's still some resources which are underutilized, but it's way much better compared to naive model parallelism. So the number of batches, for you to get the best performance, make sure that the number of macro batches equals to also the higher number of device utilization. So you need to select the correct number of macro batches along with the partition number to achieve like a linear scale. So that is quite important. Okay, but now we can face the same problem, right? Because what if the layer is too large? Layers, yes, they can take like a gigabyte or so, which is still greater than our server, which is 800. So what can we do this? How can we do this? This is where NVIDIA came up with like this technique on their paper Megatron tensor pipeline. And they say that, okay, instead of now splitting by layers, right, like one layer into one node, we can rather split by weights. And this way, we get to ensure that all of these weights fit in our server. So we don't have to face the problem of like having something too large that it can fit on our server. So scrolling down, so like I said, this technique was introduced by NVIDIA, and you can check the paper it's called Megatron. But I'm gonna sum this up with a good analogy. So you can think of like we have a model which is YXA, and we essentially we split this A into columns. So we have A1 and A2. So we split this into like the number of processes. Then we calculate yi into one process. So we're gonna have xai into one process. So on each process, we end up having something like xai, which is 1, and we end up having xa 2. So this is going to be y1 and y2, right? Then on our second layer, we utilize a technique called row parallel fashion. So what we do is that we take the B and we split it in a row fashion. So we end up having by the end, having that y1 and y2 and b1 and b2. Then we take y1 and b1, essentially we train them on a different process, and y2 and b2 on a different process. Then we apply an all reduce to aggregate the result of these two. So we add up all of them. That's how it works. But you can jump into more details. So like I said, guys, like my goal is to make sure that I implement this. I think theory is not enough to kind of like understand them fully. So I'm going to be using one of the best library, Colossal AI. It has been growing in popularity compared to other open source project, and this is like shows the need in the ecosystem for us to have these distributed training techniques. So I really like it, but we will see how it works. But they simplify most of these things for us, so that's why I think it's cool. So anyway, I want to get into like some of the techniques. They are not necessarily the same with like, when we say we're splitting the data, we're splitting the models, but rather they still help us to kind of like speed up the training a lot. So what are these techniques? So the first one is mixed precision training. So the intuition behind this, you can think of this as like we lower the precision of the model. So usually these models use 32-bit floating. So we decrease the speed roughly to 16. So the assumption is that, it is not an assumption, but using 16 bits faster, and can reduce the network bandwidth. So this is what we call mixed precision training, and essentially different numerical format in one computational workload, right? So I have to say that there is also another technique called automatic mixed precision. So this one tries to essentially figure out the correct floating point to avoid overflow and underflow. So it tried to match each operation to an appropriate data type. So this is usually what is recommended to use because it can be able to, you don't have to face like the overflow and underflow problem. Trying to do it manually, it can cause a problem, especially when you're training. So we're gonna look at another technique. Let me scroll down, which is gradient accumulation. So you can think of gradient accumulation as when we're training. So the problem is that like we have to, because of now we're distributing these models, so we have to select a small batch at some point so that we don't face the memory bottleneck, right? But now the problem, because of that, we get a bad convergence because we had like small batch size. So the idea behind gradient accumulation is that why not we add up the gradients in multiple iteration and we update the params at an interval stage. So at the like this interval stage is something that we said. It's like, okay, after this iterations we update the weights. So this way we get to solve this problem of like facing memory bottleneck due to reducing the model size. So we have, I'm just gonna go scroll down. I think we have gradient clipping. So gradient clipping is one of the known techniques, especially when we used to train recurrent neural networks. So the recurrent neural network, we used to face the problem of having exploding gradients, so what we do is that we try by all means to clip this. So we clip these gradients so that they don't like shoot high. So this way it's gonna make our training to be unstable. So yeah, I think those are the few techniques that I spoke about. Also, we're gonna touch on these techniques as we go along. But yeah, I think that was it at the high level, and I really appreciate you guys if you've watched to the end. Yeah, I think we're gonna look at the practical from all of these techniques from a practical standpoint in the next video.